Okay, everybody, so welcome to our first online video for the EE2950 Circuits SI. It's going to be a little bit of a different format, but I'm going to just work these problems out, go through the concepts, and then send this video out. Feel free to go back and forth in the video and kind of do what you got to do. All right. So our first concepts we're going to look at for exam 2 are going to be the Thevenin and Norton equivalent circuits. So with our Thevenin circuits, we're going to have our voltage Thevenin in series with our resistor that we call R Thevenin. And we have this spot here called VOC, which is open circuit voltage. Okay, so our components here are VThev, RThev, and I short circuit, where the short circuit is the current that would be induced if we put in a wire right there, because current can't travel without a closed wire. Okay. And how these are related, we have VThev is equal to I short circuit R Thevenin, so just our Ohm's law equation. Moving on over to the Norton, we're going to have a current source, and now this will be in parallel with that R Thevenin resistor, VOC. Okay. And if we were to add in this wire, this current would now bypass this resistor and would travel only through this open wire because the current was to follow the path of least resistance, where this is going to be I short circuit. So therefore we can say I Norton is equal to I short circuit. And we can get I Norton from the Thevenin. IN is equal to VThev over RThev. So those two equations are related. Okay. Scooting down. Let's look at the steps to solve these. So first step, if we see that there are no dependent sources, so that's these diamond looking ones here. So the plus, minus, and the arrow. Okay. If there are none of these, therefore we can zero out sources. And what does that mean? That means that we can take all the batteries in the circuit, we can turn them into regular wires, then we can take all the current sources and we'll go ahead and clip them out. Okay. Our second step would be to find our Thevenin, and we're going to do this by treating VOC as a battery and finding our equivalent. Okay. Then our final step is to find V Thevenin or I Norton using previous methods. So that's going to be your nodal analysis, your Ohm's law analysis, KVLs, KCLs, things like that. It's just to extract a piece of information to solve the problem. So source exchange or transformation, either way, same thing. That's where we're going to turn one source into a different source. What do we mean by that? That means that if we have a current source and a resistor in parallel with each other, we can say that that is the same as saying there's a battery with a resistor in series. Okay? And we can go back and forth between these. So, if we see there's a battery in series with a resistor, we can turn it into a current source. That's fine. And the way we go back and forth between these is going to be our Ohm's law equation, that V is equal to IR. So take what you have, find out what you don't have, change it up. Very important. You must follow this convention. And going off the page a little bit, but that's fine. Okay. So what this means that this must be in parallel. This must be in series. That's the only way we can get this to work. An important thing to note is the direction of the signs. So see here how we have our positive now pointing towards the bottom. If we want to change that into a current source, with our resistor in parallel, now we have to have our current direction pointed to the ground. Okay. That current direction pointed to the ground is kind of an indication of the voltage source current leaving this battery. So that's kind of what we use there. So same thing with up here. Current would be leaving there, current leaves there, current leaves there, current would be leaving there. Okay. Let's go ahead and move on to the next page. Okay. This page is going to be a overview of capacitors and inductors. So if we go and look at these, we have capacitors, which are modeled as a flat plate and a curved plate. Where the flat plate is the positive side, the curved plate is the negative side. Our unit for this is going to be farads, and our symbol is going to be C. And our current is going to enter in the positive terminal of the capacitor. Looking at the inductor, model as a coil, we have a positive terminal and negative terminal, where your current will enter the positive terminal. Our symbol is L, and our unit for this is Henry's, H. Our functions, so we're going to be storing voltage in a capacitor, and we're going to resist current flow in an inductor. Okay, so it wants to prevent the flow of the current from getting from this side to that side. Essentially, the current has more path to travel, so it takes longer to get over there. We'll look at some base equations. So Q is equal to CV for a capacitor, where we need to remember Q is our charge, C is the capacitance value, and V is the voltage value. important thing to note here is the charge in series capacitors are the same. Sorry. So if we have a bunch of capacitors in series, we know that they're all going to have the same amount of charge across them. Really don't have a base equation for our inductors. If we look at our combinations, so we're going to flip the resistor rules for capacitors. So for C parallel, it will just be C1 plus C2 plus C3 plus ... Then C series be 1 over C1 plus 1 over C2 plus 1 over C3 plus ... And looking at the inductors, it's the same as the resistor rules. So, inductors in parallel, 1 over L1 plus 1 over L2 plus 1 over L3 plus ... Then L in series should be L1 plus L2 plus L3 plus ... The power equation. So P is going to be equal to VI for both cases here. And notice how we sometimes how we can write I squared R or V squared over R. Like, can't really do that here because these are for the capacitor and the inductor where they don't have the resistance values on them. So looking at on what side of the formula sheet a lot of these equations are going to be. So for the capacitors, they're going to be on the left side. For the inductors, these are going to be on the right side. And I'm going to show you that at the very end of the concepts. This is a very important section, so just make sure to take note of all this. So charging and discharging. So there's the equation at the very end of the concept page that has x of t is equal to x infinity plus x times 0 minus x infinity e to the minus t over tau. So this equation is used for both charging and discharging. So we'll go look at capacitors. So what does capacitor deal with? So capacitors can be V of C at a time. It's the voltage time infinity plus the voltage initially minus the voltage infinity e to the minus time over tau, where tau for a capacitor is going to be RC. And say if we have a bunch of resistors, let's say it's R equivalent times the capacitance value, because we're going to be dissipating all of our voltage to all of the resistors, and we need the equivalent voltage. Okay. Now let's go look at the inductor side. Let's see what we got going on. So it'd be IL of T is equal to I of L at infinity plus I L initially minus I of L infinity e to the minus t over tau, where our tau for our inductor is going to be L over R. Okay. And if we notice, our capacitors deal with voltage, and our inductors deal with current. And that's kind of what we said earlier, relating back to what their functions are. Voltage in the capacitance is stored, and then current is resisted in the inductor. So this is kind of where it's coming back. Let's look at these switches. So switches are common in exam 2. So for switches, we're going to assume the circuit was in steady state before we flipped the switch, unless otherwise stated. Okay. Now, what do we mean by unless otherwise stated? So, for example, if they were to say like, V of C initially had 10 volts. So that right there is just giving us a starting value to begin with, rather than if this was operating in steady state and where it would be under different circumstances and have a different value. There's a lot of different orientations for these switches. We've got 4 examples here, just going over a couple. So this negative sign here indicates before switch is thrown. And then as time goes to infinity, you get that idea. Okay. So looking at this one here, we see that this arrowhead pointing this way. It says at time initial, we did this. So our switch is over here. Okay. So initially, you can imagine that it was closed. Then we came in, hit the switch, and then we ended up with it open. So initially it was closed, and going to infinity, it was opened. Let's go down to this example. So right before we throw the switch, so here we can see that this is hanging out up here for us. Then we come down and throw the switch, and it's going to push the switch in a direction such that it'll end up closed. So initially we were open, and we let this run to infinity, it will remain closed. Okay. Coming to this next example here. Sorry, everybody, my computer is acting up a little bit. Okay, so initially we can see that this is closed, right? But then we're going to come in here, hit it with this arrow, and we'll end with it hanging out up here. So we can see initially it's closed, and now run to infinity, it will be open. And you'll notice that these two are the same thing. This is just a different orientation for them to be in. And finally down here, let's look at this one. So this is now a situation where we have two terminals and a switch. I'll call this one A, I'll call this one B. So we can see that initially we are connected to A. It's pretty easy to see that we're right there. But then we're going to come in, hit it with this arrow. Then now this will go away. And this dotted line, which indicates a direction that it will be in, will turn into a solid line. And we are connected to B. So keep an eye out for this one, because sometimes they like throwing a difficult question like this on there. And I believe that is it for the concepts. I'm going to scroll down to the bottom, and let's go and take a look at the sheet that I've attached here. Okay, great. So, looking at this equation sheet, we see that, wow, this thing is acting up today. See here, in this blue box, these are going to be our capacitors. In this box, these will be our inductors. Okay. So we have equation for current, voltage. This W here is energy. This is our Q is equal to CV equation. Same equation, just lowercase. There's another current equation. This is just from what we had at the beginning of the semester. The difference in charge over the difference in time is what current is. But we can also extend that to say that the capacitance times the change in voltage with respect to time is also equal to the capacitance value. Would like you to keep an eye on this one right here. This is a capacitance equation. So this is how we determine the capacitance of a capacitor. Where this A is the area, and that's area of plates, and D is the separation distance. And that weird little epsilon value there, this is known as the dielectric constant. Okay. So you're going to need this value in order to solve the problem that we have in this SI and potentially on the exam. You'll notice the power equation here. P is equal to IV VI. That applies to both the capacitor and the inductor. Now, here at the very bottom is where we have our charging and discharging equation that we wrote in our concepts. And underneath, they provide the time constants, the tau values. So RC L over R. Okay. They just don't give you the subscripts there, but I mean, you can see the capacitance and then the inductance value there. So that's it for the concepts. In the next video, we're going to look at the actual problems themselves. I'll see you there.